Hey guys, what's up? My name is Gabe and this is Games with Gabe, and this is the next episode in the font rendering series. So, if you remember from the last tutorial, we got to a point where we can render text pretty good, except we have one big problem, which is if you blow it up to any size, say you generate a 32 size pixel font and you scale that up, then you get this blurry text. And it may not be as visible on your screen as it is on mine, but this is a problem, and so there have been a lot of different research efforts to try and get text to scale up and not lose visual fidelity. And one of those research methods that we are going to take a look at today is something called a signed distance field. So the whole concept of a signed distance field is, instead of generating the bitmaps like we have been, just generating straight up images of the actual font that you're using, you generate an image that looks like this. And you can see when this is zoomed out, you can sort of see the shape of an A, but as you zoom in, you can see that it has this weird haze around it, okay? And this haze is something called a signed distance field. It's basically a distance from where you are here to how far you would have to get to be at an actual edge of the letter A rendered in whatever font that we used. Now, the one downside to generating these is that it takes a while. It's kind of a long process, and we'll talk about why that is. But the main benefit of this is you can actually scale up and not lose your visual fidelity. So this is the same font, or actually this is a slightly different font, but rendered at 32 pixels using the signed distance field. And you can see that it retains a pretty nice quality, with another exception of the edges being a little bit more rounded. And we'll talk about why that is too in a minute. We won't actually get to this point yet. This is from a different project, but we will be getting to the point where we are generating the signed distance field, and I'll talk about how you can actually render using this, and then we'll go ahead and implement that in the next episode. Anyways, let's talk about what signed distance fields are, how they work, and how we're going to go about implementing them. All right, so what exactly are signed distance fields? Well, basically, what we want to do is we want to store our fonts in small 32 by 32 pixel sized textures for each glyph, right? That way we can save memory and use that for like our assets, which actually matter, like game characters and stuff, which we want to be higher fidelity. But we want to maintain the visual fidelity of a 2K font texture, right? Or 4K. How in the heck can we encode it so that we have 2K data inside of this small 32 by 32 pixel data? Well, the answer is by using signed distance fields and the GPU's linear interpolation. Now, first of all, what is linear interpolation? Let's say we have some quad that we're trying to render this glyph to, the letter A. And on the screen, it's just 4 coordinates like this in your world. And you want to map this 32 pixel by 32 pixel texture to this. But let's say this is bigger. This is 256 pixels by 256 pixels, right? So what the GPU does is it automatically interpolates all this data, and it sort of stretches it, right? So it'll stretch the texture up to this big. And then if we tell it to use a linear approach to interpolating, it'll basically just stretch it so that it kind of blurs the pixels in between. Say this pixel is in between 2 pixels here. What does it do? It just interpolates between the 2 pixels over here. And so basically we can use this to our advantage to sort of store a lot more data than is actually in this 32 pixel texture. The way we can do this is we can store distances inside of these 32 by 32 pixels. And what the distance is if we mapped this to this, so say this maps from 0 to 0, and then the end maps from 32 to 2000. This maps from 0 to 0, this maps from 32 to 2000. We're basically saying if we were to map this into a very large texture, how far do we have to go until we hit a pixel of a different color, or a white pixel in this case, right? The font. And so what this looks like in actuality is, say we are generating our SDF here, and we want to figure out what color this pixel should be. Well, what we can do is we can map it to this 2000 by 2000 pixel, which would end up being somewhere right here. And then we can say, hey, how many pixels away is this from this letter? Well, if we look at that, that's going to be something like, I don't know, 200 pixels. So we have to go 200 pixels to get to the closest pixel of a different color. Well, what we can do is we can normalize this. So instead of saying 200, we can give this a different number, which sort of represents it more, something like 0.1, right? We're 0.1 close. And then if we are on the pixel, what we can say is this is 0.5. And then if we're inside of the pixel, so now we're going the other way, we can say this is like 0.6. what this gives us is automatically all of the edges will be 0.5. So that's one good thing. So if we were to sample directly on the edge, it would be 0.5, and then inside of here, it would be 0.5 or higher. All the values inside of here are going to be higher than 0.5. So this will be 0.8, but it will never go over 1. So like this could be 1, but it will never get higher. Outside of the letter A, it will always be less than 0.5. So this would be like 0.3 because we have to go 0.3 to get to the nearest edge. Now, this gives us some clear boundaries of what we can use. So if we are blitting this texture onto this quad, which is bigger, and say we are trying to figure out what color to color this pixel, right? And we don't really know exactly what color to color it, but this says, hey, this pixel right here, that's like 0.49. What that tells us is we can draw it in an anti-alias color because we're so close to the edge that we can just blur this and it will look good. And then say we sample directly on the letter. Well, then it would say this is 0.7. And then we could say, okay, just draw this whatever color they want to draw the font, and so on, so forth. This gives us a ton more data to work with. We can pack a huge amount of data into this 32 by 32 pixel texture. It will come with some artifacts though. So the artifacts that we'll get is, since we are basically sampling these square-ish regions from the texture to generate this, right? So 1 pixel here is a very small square, but when we blow it up to the scale, it turns into this huge region. What ends up happening is we get kind of these weird curves, and it will kind of be like curved like this. And the reason we get this is just because we're blowing up this data and we're trying to pack it into as small a space as possible. And there are ways to get around this, which we will talk about in a little bit. But how do we generate this SDF? So how do we get all this data and pack it into this 32 by 32 pixel texture? Well, what we can do is we can basically say, hey, let's go through each of these 32 pixels. All right. So we'll start at 0, go to 32, then go to the next line, go to the next line until we get all the pixels. What we're going to do is we're going to map that pixel onto this range. So say we're in the middle, 16. Well, if we were to map that to this range, it would be the 1,000th pixel, right? Because that's directly halfway between this. And so we'll map it to 1,000. And then what we'll do is we will sample up to half the texture size. So we'll sample a region of 1,000 by 1,000 pixels, which that isn't 1,000 by 1,000, but imagine it is. And what we'll do is we'll look through all of these pixels and figure out which pixel is the closest one to this one that is a different color. In this case, that would be this pixel right here, right? Because that is the shortest distance, if I drew that line correctly. And so this would end up giving us some distance, which is the shortest distance we have to go in order to get to a pixel of a different color. Actually, it might even be this one. So it could be that one. Whatever, it'll pick one that is a different color. We then use this data after we found the minimum distance to get to a pixel of a different color. We normalize it. So we'll say, okay, in order to get this on a range of 0 to 1 instead of whatever this would be, which would be 0 to however big this is, which is in this case 1,000. Then what we can do is we can say, hey, in order to get this cool feature that we talked about where anything less than 0.5 is black, anything greater is white, what we can do is say if this pixel was black when we started, just multiply it by -1. If it was white when we started, so say we were sampling this pixel, then multiply it by +1. What this will do is it will then map this to a range of -1,000 to 1,000. Okay? And so this basically gives us a range now where anything below 0 is a black pixel, anything above 0 is a white pixel, and anything that equals 0 is on one of the edges. Now that we have this range, we can very easily map this to 0 to 1, once again, just by adding 1. So if we just add 1 and then divide by 2, then that will map it from -1,000 to 1,000 to 0 to 1. And it so conveniently happens to map it so that this is now 0.5. These distances are less than 0.5, and anything inside of here is greater than 0.5. That's basically all we have to do. So we sample a region. We find the closest pixel that's of a different color or a different state. Then we map it to a range of 0 to 1,000, then -1,000 to 1,000, then 0 to 1, which will end up giving us some color here and give us that distance field I talked about earlier. And just so that we have a visual one more time, you can see that this is what it will end up looking like. And you can clearly see all the values less than 0.5 are black here because we're not actually anywhere near it. And then as we get closer to the value of 1. And all these values above 0.5 here indicate that we are directly inside the pixel. And you can get that rough outline of an A. this is really cool, and it will greatly improve our rendering fidelity for such a small texture size. Now, the last thing you have to worry about is rendering. So how do you render this? It's really simple. We just use these rules we created, and we basically say inside of our shader, if it's greater than 0.5, color it whatever the color the user wants. If it's between 0.48 or some other value and 0.5, so if our X or whatever our pixel color is between those two, we'll just leave it whatever it is. So we'll blend the alpha so that's 0.48 to 0.5, and that will give us some anti-aliasing, so AA. And then if it's less than 0.48, then we don't color it. We just discard the pixel or color it as black. And that's all you have to do for the shader. No tricks that would make it extremely computationally expensive for the GPU. It's just straight up sampling the texture and then doing a few different conditions. All right, so let's actually try and code this and see if we can start generating these SDFs using Java. And we are also going to use FreeType for this just because I think STB, he has some warnings inside of his library. He's like, this isn't actually the greatest tool for this purpose. You should probably use a different library. So I wish LWJL bundled FreeType with LWJL by default. Instead, they just do STB. We will be adding FreeType manually, and I found a Java binding that we will use just because I think it is a little bit more stable than his library. His library is still good. You could still use his library to do what we're about to do as well. Anyways, we'll talk about how to import FreeType and then how to do this whole SDF generator. All right, so first things first, we need to get our binding to FreeType into our project. I am gonna have a link to this in the description, but basically what we're gonna do is go to this guy's releases, and then I'm gonna go to 1.1, and I will download this FreeType.jar. Then I'm gonna save this to our project's path, so font rendering, and then I'm gonna create a file in here, call this libs for libraries, and then I'm going to save it inside of here. Then we're going to go ahead and also install the DLL. So we will install this DLL. We will hit download, and then we'll go and create a new file in here. We'll call this natives, and then create another directory, call this Windows, and then save this right here. If you're on Mac or Linux, by the way, too, you will have to manually compile the jar and compile FreeType. Or you could just go to FreeType, and then you could get the binding directly from them. So they have downloads over here too. And then you can go through their download process for Mac or Linux, and you can compile it manually if you have to by going to their GitHub repository here. But I do believe, yeah, they have releases here as well. Anyways, we will just be using this DLL for my project, and if you need to get the other one, then you should do that right now as well. Anyways, so we've basically just downloaded these files into our project, and now we want to get our IntelliJ project to recognize these. So the first thing we're going to do is we're going to go ahead and edit our build.gradle file, and we're going to go ahead and add in a dependency in here, and this will be for FreeType binding, or actually just the FreeType jar, which is the binding, I guess. And then we're going to go ahead and type in implementation, file tree, libs, which basically just says look in the libs directory that we created, and then we'll say include anything that has .jar as the file extension. This way we get those libraries implemented, but right now if we were to try and run this, if you import those changes and then you go ahead and hit Shift F10 and try and run this, actually it'll run just fine until you actually try and use the library. So we'll go into here just so that we know when we actually get this working. If you go ahead and just type in library equals new FreeType, or actually I'm sorry, FreeType dot create new library, and then you can say system.out.println version plus library.get version. And then if we were to do this and hit Shift F10, what you'll notice is that we actually get a build exception. I don't know why it still ran there, but if you notice here, I get this exception. It says unsatisfied linker error, no FreeType-JNI-64 and java.library.path. So basically what we have to do is we have to add our path to here. And the way we can do that is if we just go up to run and then edit run configurations or edit configurations. And then if you just go into the VM options and type in -D, java.library.path equals, remember no spaces, /libs/natives/windows. What this will do is it says, hey, Java compiler, just remember we also have natives or DLLs inside of this path here. And then it'll go ahead and look for any DLLs inside of this path, as well as other paths that it has. Then you can go ahead and hit OK. You can't really see it on my screen, but it's right there. And if we were to hit Shift F10 one more time, then you will notice that we don't get any errors down there. And if we actually take a look, we see that it says version 2.9.1. So we now have FreeType imported and it is working correctly. Now, if you want to know how to use the FreeType library, you can go ahead and check out their documentation, which is great. He also has some little examples of how to use the FreeType functions in here, because it is a little bit different than if you're using their documentation directly. But he has this sort of getting started. Make sure to do library.new library, and then make sure to do library.delete to clean up the memory. And then he also has these things to create font faces and all of that stuff. And let's go ahead and create a new class. We'll just go into here and create a class called SDF. And this is just going to be a completely static class full of some functions that we will use regarding SDFs. So the one function that we will be using a lot is public static void generate code point SDF, or code point bitmap, I guess. We don't have to say SDF because we know this is an SDF. And then we'll take in an int code point or character. So this is the character we're trying to draw. String font file. So this is the path to the font file. And then int font size. And that is the size of the SDF that you want to happen. So like if you want a 32 pixel by 32 pixel SDF to be generated, that's what you would pass in there. Then we're going to go ahead and just make sure we can actually use FreeType. So we'll say library equals FreeType.new library. And then we'll go ahead and make sure to write library.delete so that we don't forget to do that as well at the end of the function. And then we're just going to go ahead and say assert library does not equal null, which won't actually do anything because we don't have assertions enabled, but it's good to have that there because if it does fail, then that's not good. And let's actually, instead of doing this library.delete, I'm going to create a helper function down here. We'll say private void free, and this will take in a library, and then we'll take in a font as well in a little bit. But let's just call the FreeType binding directly. So we'll say ft done FreeType, and then if we go ahead and hit Alt Enter on this, then we can say import static method, and then we'll import it from here. And if you hit Control P, it takes in a long, which is a pointer. And I hate how he has the functions abbreviated in here. If you actually look at his documentation, he actually tells you what this is. So it says long library, which is the library pointer. So yeah, but anyways, we'll just say library.getPointer. Do like that. That makes it very explicit what we're doing. So we just free the library's pointer. And then instead of calling delete, I'm just going to say free library. Next, like I said, let's make sure that we actually can do this. Oh, and make sure to make this a static method as well, because otherwise we can't use it. Anyways, let's go ahead and create a font using the font file that they passed in. So we'll say face font. So they call fonts faces in FreeType, but we'll just call it a font. We'll say is a library.new face, and we'll pass in the font file. And then you'll notice it takes in an integer I, which we're going to pass in as 0. And this integer I is kind of weird. If we actually look at his documentation, you'll see if we look at right here, it says the string, the file, and then int face index, and he seems to just use 0 for his face index. The way you do it in actual FreeType is it gives you the index. I don't really like the way this works, but we'll do it this way. And then if you create more than one font, then you may have problems, and we'll talk about how to solve those at a later time. But anyways, we'll just do 0, and then if you were to create another font, you would have to increment this to 1, and then if you did another font, then increment it to 2, or yeah, and so on and so forth. Anyways, after this, we're going to say ft set pixel sizes, and if you look at this, it takes in a long L, which is the library's pointer, so we'll say, or I'm sorry, the font's pointer, so we'll say font.getPointer, and then it takes in V, which if you look at FreeType, they actually set that as 0. Can't remember off the top of my head what that is exactly, but V1 is the font size that you want to use, and we'll set this as our font size for now because we just want to test this and make sure it works. So this should allow us to generate glyphs at 32 pixels, whatever we pass in. And then we'll say if ft load char font.getPointer. So basically what we're going to do here is load a character, char code point, and then ft load render, and we'll talk about what all this does in just a second. Hit Alt Enter to import that, Alt Enter to import that. Then we'll say system.out.println FreeType could not generate character, and then we'll say free the library, and now we have to free the font as well, and then we'll return. And down here, we will make sure to free the library and the font as well. Let's just finish up this free function real quick. So we'll take in a face, which is the font. And then down here, we'll say ft done face, pass in the fonts pointer. That way we clean up all of our memory every time we fail. So what is this ft load char? Well, basically this loads a character. So we're saying we want to draw this character that they passed in. So go ahead and draw that to whatever your global state is, and then it goes ahead and draws it. Simply said ft load render. That's all that does. Now we want to get the actual glyph, the bitmap information, right? We want to actually see what the pixels it drew were. So we'll go ahead and do that now and see if we can understand this correctly. So we can first of all get the glyph width by saying font.get glyph slot .get bitmap .get width. And what this does is FreeType is sort of like OpenGL in the way that you interact with it, where you are affecting global state every time you call functions. So we call this set pixel sizes, that affects global state. We call this load character, that affects global state. Now that we've loaded this character, we can get the width of the character by calling this function. And then we can also get the height of the character by calling font.get glyph slot, which is the currently loaded glyph, .get bitmap, .get rows, which is just the height. And then let's say we want to actually get a hold of the image that they drew. Well, we can get a hold of that too. We can say byte buffer, which is what they drew it to, image buffer equals font.get glyph slot .get bitmap .get buffer. Now we've gotten a hold of the buffer that they drew to. Let's write this out to an image just to make sure that it is drawing whatever character we passed in. So what we're going to do is we're going to say for int, or actually we'll just say while true, because this is temporary and we're just testing something real quick. We want to get bytes out of this byte buffer. So what we can do is we can say byte b equals image buffer dot get. And what this will do is it'll get us a byte, and then it'll increment this byte buffer forwards one. Let's also keep track of our x and y. So we'll say x equals 0 and y equals 0. And then we're going to write all of this byte buffer data to an image buffer, just so that we can write this out and actually see what's going on. Or I'm sorry, a buffered image. And then we'll say this is a test image equals a new buffered image. We'll give it the glyph width, the glyph height, and then we will give it buffered image dot type int argb. So each pixel in here is one integer of argb type. Now we actually want to fill this image, so we have this xy, and what we'll do is we'll say byte b, we get the byte at whatever value we're at, and then we'll say int argb equals, and we'll basically just do b. Let's actually cast this to an integer just because this makes it a little bit easier. We'll say this ANDed with 0xff just to make sure we get the byte as a byte. Java's type system is weird and it'll do weird things if you don't do that. So then we'll just basically say b shift left, or actually we'll do 255 shift left 24. So alpha will always be white or full, and then ORed with the byte shifted left 16, ORed with the byte shifted left 8, ORed with the byte. And that will basically just get us an RGB grayscale of whatever image they gave us. And then we'll say test image.set RGB at XY, whatever XY we are at, ARGB. We just basically go through, set each pixel to a color that we want to write to. And then we'll say if X is greater than or equal to the glyph width. And then we'll say X equals 0, Y plus plus. And then if Y is greater than or equal to the glyph height, then we will just break out of this loop because we are done writing to the picture. And then we just want to try to write this picture out. So we'll say file output equals a new file, test.png, import those. And then we'll say image io.write test image. So that's what we want to write. And then it's a type PNG, and the output is the output that we want to write to. And then we'll catch an IO exception E and just say e.print stack trace. Okay, so what this should do is basically just draw the letter. We're basically just getting the buffered image that they give us, converting it to an image for Java, then writing that image as a PNG just to see and check our knowledge and make sure this is all correct. So let's go into our window, and right before we run, let's go ahead and just say sdf.generate code point bitmap, capital A, and I'm going to use c/windows/fonts/arial.ttf, and I'll say at 128 pixels. So this should generate the letter A at 128 pixels big, and I'll move that to here. Oh, and we're not in Python or JSON, so I need to use double quotes for those. Okay, anyways, then if we hit Shift F10, let's see if we get that. And I believe that byte buffer is read only, which is why we're getting that error. Can't remember completely, but let's go ahead and just place it into a byte array just in case. So we'll say byte glyph bitmap equals a new byte, and its size is going to be the glyph width times the glyph height. Then what we're going to do is, instead of doing this whole byte buffer equals this, what we're going to do is we're just going to say font.getGlyphSlot.getBitmap.getBuffer.get, and then we're going to put it inside of glyph bitmap, and we're going to go ahead and say that we only want to put up to glyph width times glyph height in there. So what this does is it basically says, I'm going to move this to a new line. Oh, and we forgot the offset, so offset is 0. This basically says put this buffer inside of this byte array. That's all we're doing there. And then instead of looping through the image buffer, we're going to loop through every byte inside of here. So we'll say for byte B inside of glyph bitmap, change this while loop to a for loop. Then we're going to do this, and I'm just going to get rid of that. And we'll actually say int B equals pixel anded with 0xff, and then we'll just change this to pixel instead of B. That way we get that. And we should be good now. Let's try this and make sure it works. Okay, so that worked out fine. Yeah, I forgot that that buffer is read-only, so you can't really just directly read from it. But we get this test.png, and if we open this up, it does not look like we got our image. Oh, and that's because we never increment x, so I forgot to put that x++ in there. Now if we run this, we should see that we get the letter A printed out as an image. Let's just make sure that this works. There we go, and you see that we get the letter A nice right there. And let's go ahead and just make sure this works for sure. I'll increase this to a 4K size. If we hit Shift F10, run this again, you'll see it takes a little bit longer just because that's a bigger texture to generate. But if I go ahead and take a look, we get a much higher quality letter A. Cool. So we can be confident that FreeType is working correctly. If we go back into here, I'm going to relower this to just 32 because that is the final form we will want. We have access to a glyph bitmap, and we can now scale this up to 4K, 2K, 4K, and then we can get all the pixels here. So we should be able to do everything we need to do now. So I'm going to add a few different variables up here. We are going to say we need integer padding, which I'm going to set to 15. So 15 pixel padding around the letters. Int upscale resolution. So this is what resolution we want to scale it up to. I'm going to set this to 512 because that's pretty quick on my machine. You may want to go to like 256 or 128 depending on your machine just while you're testing to make sure you get it right. And we'll say int spread equals upscale resolution over 2. And the spread is basically how far we will search within this image to find another pixel. And if we do half of the size of the resolution, then we should get an appropriate spread to make sure we always find the closest pixel of a different state. Okay, so we have those, and now we want to basically create a mapping system and everything, okay? So first thing I'm gonna do is put a few more spaces in here, and we're gonna get a lot of scale values, right? Okay, so first thing I'm gonna do is say system.out.println glyph width, and then we're gonna say glyph width, and then system.out.println glyph height, and I'm gonna do plus glyph height, just so that you can see something. So if we print out this, remember I set it to 512 for the pixel size, but you'll notice we actually get 23 by 23, and that's because we're not setting the pixel size to the upscale resolution. So instead of doing this, we're gonna say set the scale to upscale resolution instead of the font size that they chose. Now if we run this one more time, Once again, set it to 512, but you'll notice it says the width is 344, the height is 367. Why? Well, that's because when we actually generate the glyph, the letter A doesn't actually take up 512 pixels by 512 pixels. It's not square. And so FreeType is going to give us the glyph in the smallest possible space that we can do to contain it while setting the overall line height to 512 pixels, which gives us a width of 344 and a height of 367. So we're going to create a scale factor, which is basically how big from this width to 512 do we get and how much from this height to 512 do we get. So we'll go ahead and say float width scale equals float glyph width over float upscale resolution. And we'll say float height scale equals float glyph height over float upscale resolution. This way we can sort of scale between what our upscale resolution is and what the actual width we got was. Then we can say int character width. So this is basically going to be our output character equals int float font size times width scale. So now the user wants to create this a 32 pixel SDF, right? So we can say, well, if we use the same scale that we got from FreeType of the glyph width to upscale resolution, then we can scale the font size that the user passed in by that scale, and we'll get the appropriate width of our character. And we'll say the character height is the same deal, except we're just multiplying font size by the height scale. And that will give us an appropriate width and height for our 32 pixel character. Then we're going to go ahead and say int bitmap width. So this is the output bitmap that we're going to create equals character width plus padding times 2, right? Because we have padding on the left and padding on the right. And then we're going to say int bitmap height equals character height plus padding times 2. Once again, we have padding on the top and padding on the bottom. Then we're going to go ahead and say float bitmap scale x equals float glyph width over float character width. And this is basically saying, okay, so we have that glyph. How much bigger is the FreeType glyph, the upscaled font, than our output font? This is so that we can map from our font to their font, right? From pixels in our coordinate system to pixels in there. Think of it like Minecraft in the Nether. You have to divide by 8 because the overworld is bigger than the Nether. Same here. The glyph is bigger than the actual output bitmap that we want to create. We'll do the same thing for y. So we'll just say this equals float glyph height over float character height. And then we're going to go ahead and create some space for the bitmap. So we'll say bitmap equals a new int bitmap width times bitmap height. This is our output. This is our SDF. This is what we want. So you could label that SDF bitmap if you wanted to. Then we're going to loop through all the pixels in this bitmap. We're going to say for int y equals negative padding until y is less than bitmap height minus padding. Okay, or we could do this a different way. We could say character height plus padding y plus plus. So basically what we're doing here is we're looping from negative padding to positive padding to give us a range like as if we're going from a little bit below the character to a little bit above the character. And then we're going to say for int x equals negative padding till x is less than character width plus padding x plus plus. This way we go from behind the letter, so a lot to the left of the letter, to the right of the letter, right? Because if we look at this letter, this box encapsulates it perfectly. Well, we actually want to start off a little bit over here and a little bit over here. So we have to start off negative and go beyond its width, and we have to start off below and go beyond the height. Anyways, now that we have this, we want to be able to map these pixels into the actual big glyphs range. So we can say int pixel x equals int, and I'm going to say map range from, so we're going to map this x value from negative padding to bitmap or character width plus padding. So the current range we're going from is negative padding to character width plus padding, right? That's the range we're going from right now. The range we want to go to is negative padding times the bitmap scale x, and we want to go to the character width plus padding times the bitmap scale x, right? So we basically just want to create a function that goes from one range to another. So the range of our small character is only from negative padding to here, but we want to map it to the overworld coordinates, which is basically what this function will do, okay? Then if we say int pixel y, we can do the same thing. We'll say is an int, and we're going to map range, the value y, we want to map from minus padding to character height plus padding. That's the input range. We want to map it to this output range, which is minus padding times bitmap scale y to character height plus padding times bitmap scale y. Okay, so let's create this map range function, which I'm not going to lie, I took directly from Stack Overflow because I cannot be bothered to create this function every time. Every time I need it, I cannot remember how to create this. So we'll say map range, and I'm going to do something that I hardly do and just copy paste. So I'm going to go ahead and copy this and paste it here. So we take in a value, we take in the in min, so the in minimum max. So this is the in range, and this is the out range, right? And then this is the function that basically maps from this range to this range. This value from, yeah. So just copy that, just a math function. There's nothing special there. So now that we have our pixel x and pixel y mapped into the big glyphs range, we basically want to find the nearest pixel. So we'll say float value equals find nearest pixel of a different state, obviously, of pixel x, pixel y. So those are the pixels we're starting if we're mapping into the big characters range. And then we will pass it the image or the glyphs bitmap. So I'm going to copy that, glyph bitmap. And we want to give it the glyph bitmap's width and height. So we'll say glyph width, glyph height, and then we also want to give it the spread factor. So we will create this function. I'm going to go ahead and move that to a new line as well. It's all getting kind of cluttered here, but don't worry. So we basically want to find the nearest pixel to this x and this y of a different state inside of this bitmap. And we give it the width and the height and the spread just so that it has all that. Let's copy this. We'll go up here and say private static float, paste that, and then we'll create the function. These are going to be an integer. This will also be an integer. The glyph bitmap is a byte array. The glyph width is an integer. Glyph height is an integer. Spread is an integer. Okay. So now we just need to create this function that basically looks for the nearest pixel of a different state. So what we're going to do is we're going to say int state. This is just the state of the pixel at pixel x, pixel y equals get pixel, pixel x, pixel y. We'll pass in the bitmap. I'm going to change this up a little bit because now we're operating on a bitmap with a width and a height. Bitmap, we're going to give it the width and the height. And what this will do is just give us the pixel, or 0 if it doesn't exist. So we'll say private static int get pixel, takes in an x, a y, a bitmap, and a width, and a height. And we'll just say if x is greater than or equal to 0, and x is less than the width, and y is greater than or equal to 0, and y is less than the width. So if we're in the range of this bitmap, then we'll return bitmap x plus y times width, which basically just maps this from x to x plus y times width. And then we'll go ahead and say 0xff. So we're basically just mapping from 1D coordinates to a 2D coordinate here, and then we're going to AND it just so that we don't get any weird errors. And we're going to do one last thing here too. We'll say if this equals 0, we'll return 0, otherwise we'll return 1. So the values right now can range to quite a few different values. And we basically just want to clamp it. So if it is 0, we want to do 0. If it's not 0, we'll just say 1. So it's basically we're saying it's an off-on state. And then we'll return 0 if we're outside the range, because clearly we can't have an on pixel if we're outside of the actual font's range. So we get that state. Next, we're going to say int min x equals pixel x minus spread. Int max x equals pixel x plus spread. Int min y equals pixel y minus spread. Int max y equals pixel y plus spread. So we're creating a square region around the pixel they passed in to search through for the next pixel that's going to be the closest one. And we're just going to do a very generic linear search for the smallest distance. So we're going to say the minimum distance equals spread times spread. We're going to keep it as the distance squared. So if you know Pythagoras theorem, then you know that c squared equals a squared plus b squared, or a squared plus b squared equals c squared. We're going to be keeping track of these c squared distances, right? Because the length of a vector is just a squared, the square root of a squared plus b squared. We're going to keep it in the squared form and then take the square root at the end. That way we save a bunch of unnecessary square roots, which can take up a huge amount of time because this is a lengthy operation. Then we'll say for int y equals min y, until y is less than max y, y plus plus. For int x equals min x, until x is less than max x, x plus plus. Int pixel state, so this is the state of the pixel here, equals get pixel. X, y, bitmap width, height, and that will get us that pixel state. And then we'll say float dx squared, so the distance in the x direction, is x minus pixel x times x minus pixel x, float dy squared equals y minus pixel y times y minus pixel y. And then we'll say float distance squared equals x squared plus y squared, or dx squared plus dy squared, right? That's just Pythagoras theorem right there, except we're keeping it all squared instead of taking the square root. And we'll say if pixel state does not equal pixel state, then the minimum distance equals math.min, the distance squared, or the minimum distance. So we basically say if this distance is smaller than our current minimum distance, which we set it to the max distance possible, then we'll set it to this one. So we basically just look through the pixels if it's a different state, and if it's closer, then this is the new minimum until we search through all of the pixels. It's inefficient, but it works. Then after we finish looking through our region, we'll say min distance equals float math.square root of the minimum distance. And we'll say float output equals, now this is where it gets a little bit weird, we'll say min distance minus 0.5 over spread minus 0.5. So we're normalizing it to 0 to 1. Right now it's on a range 0 to spread. This normalizes it to 0 to 1. The reason we subtract 0.5 is because this gets rid of weird integer flooring errors and stuff. You could probably get away without doing that actually, if you wanted to. Then we'll say output times equals state equals 0, -1, otherwise 1. So what we say here is if we have an off pixel, we're going to multiply it by -1. So if we started inside a black pixel, then we want to do -1. If we started inside a white pixel, then we want this to be +1. So now we're mapping from negative spread, or -1 to 1 is the range we're mapping to now. Then we want to map from -1 to 1 to a range of 0 to 1. So we'll just say return output +1 times 0.5f, which does exactly that. Now we have a function that finds the nearest pixel, hopefully, right? So if we have a 2D array, this should find the nearest pixel of x and y to this and return that value. So now we basically just want to put that inside of our bitmap that we're keeping track of. So we'll say bitmap x plus padding plus y plus padding times bitmap width equals int val times 255.0f. We're doing x plus padding because otherwise we'd get an index out of bounds exception, right? Because we're going from negative padding to character height plus padding. So what we actually have to do is add padding just to make sure we go in the correct 0 to width range and 0 to height range. And then this is just a normal 1D or 2D to 1D linear expansion of an array. Then we will go ahead and let's write this bitmap out as an image, okay? So instead of doing glyph width and glyph height, we'll say output width, I think is what I called it. No, we called this bitmap width and bitmap height. So we'll copy those. And then we basically just want to go through our bitmap and copy all those values. So instead of going through the pixels in the glyph bitmap, we'll say for int byte as bit int inside of our bitmap, which is our output. This is our SDF now, okay? We're going to say int argb equals 255 shift left 24, keep alpha constant. We'll do byte as int, shift left 16, shift left 8, and then there. And then we'll just set that once again. We'll have to change this to bitmap width because we're no longer going through the glyph. Change this to bitmap height. That caused me a ton of trouble and I thought I was doing my program wrong. But yeah, let's see what happens now. If we do this, it's going to take a little bit on your machine and it could take quite a while depending on your machine. So don't worry. Then we're going to hit test.png and just see if this worked. It did not. I must have done something wrong here. Oh, and I think it might be this line right here. If we go up to get pixel, I did y less than width. That should be y is less than height. Let's see if that fixes it. Run this one more time. This is why I said to start with a small image too, because it's really annoying to have to wait a long time while doing this. That did not fix it either, but that was a bug. Let's see if we get it next time. I don't know if you guys saw this while I was writing this, but pixel state does not pixel state is always false. I don't know why I didn't notice that. If pixel state does not equal state, then we want to do that. Okay, let's see if that fixes the bug that we were having. We get this, and then if we open up that image, there we go. We get a proper SDF image for this bitmap. Now, if you wanted a higher quality SDF bitmap, what you would do is you would increase this upscale. So say I wanted to make it higher quality, I could increase to 1024 pixels, but you'll see it's already taking longer, and quite a bit longer, okay? That was just for one character. Remember, you have to generate a whole font full of these, so you want to be really careful about that. And this will actually create a little bit better of an SDF at 32 pixels big. And you could increase the padding, do all sorts of tweaks if you want to. Anyways, this video is running for way too long though, so we have generated these bitmaps. In the next episode, we're going to actually use these sign distance fields and render them to see the quality difference we get. All right, so I'll see you guys then. I hope you enjoyed this. If you did, please hit like and subscribe, and I'll see you guys next time. Thanks.